So we're going to take a little bit of a break from matrices, and we're just going to talk about solving nonlinear systems. So what I mean by nonlinear systems is I've got, up until now, we have only solved a system with two variables and two equations where both of the equations were lines could be put in the form y equals mx plus b. And remember, a line is where all of the exponents are the first power, right? Everything is to the first power here. So here I've got a bunch of things being squared in my first equation. So this is actually the equation of a circle, but we'll get to that in another chapter. So what we have here is we have a circle with a line that may or may not be touching it or crossing through it. So we're just going to see, what happens as we solve for this. So we're going to use the same old tools that we've been using before. We can either use substitution or elimination. Now I prefer to use substitution when I can easily identify one variable or set aside one variable. So I can easily solve for y, right? I get y equals negative 3x plus 1, right? Just by solving for y. And then what I can do is I can put that in parentheses, and then I can take it and plug it back into my other equation. So then I get x squared plus negative 3x plus 1 squared equals 5. And then when I square this all out, I'm going to let you do that, but when I do that, I get x squared minus 9x squared, plus 9x squared, minus 6x plus 1 equals 5. Now I've got some x squared terms I can combine, right? So I have 10x squared minus 6x, and I can bring that 5 over for a minus 4. And now I have a GCF with of a value of 2, right? 2 goes into everything. So I have 5x squared minus 3x minus 2 equals 0. And now this does factor. I can either factor or use quadratic formula, whichever you prefer. This one actually does factor into 5x plus 2 and x minus 1. And we set all, and we set all that still equal to 0. So now if I have two factors, right, I've got two things in parentheses, those are factors, and if I set one of them has to be equal to 0, so when I do that I end up getting x either equals negative 2/5 or x equals positive 1. So now I need to solve, just like before, I need to solve for my y value. So I'm going to take, remember there are two values here, so we're going to take them individually. So I'm going to start with 1, and I'm going to go back into the second equation because I would certainly rather solve for y where I don't have things being squared. It's your choice. You can go back into either one, but I'm just going to go back into that second equation. So then I get 3 times 1 plus y equals 1, and then I end up getting y equals negative 2. I'll let you finish that work. So one of my answers is, is 1 comma negative 2. So that is one answer that I have. And then my second answer, when I plug in negative 2/5, I'll let you do that work. So when I get negative 2/5, my y answer ends up being 11/5. Again, all I did to find that was I plugged negative 2/5 in here for this x and then moved it over and got my y value. So these are my two answers. Now, this is the critical difference between systems of equations where they're both linear and where they are not linear. Because they are nonlinear, we are talking, and we're going to get into some more complicated examples, and you're going to have some more for your homework to do, but because they are nonlinear, we are probably at some point either squaring or possibly square rooting both sides of the equation, in which case you could end up with extraneous solutions. So it is critical, it is really, really important with nonlinear systems that you test both of them. So you have to test your answers. So please test your answers into both equations. And the way that we do that is we take, I'll take this 1 and negative 2 and I'll plug it back into this equation and make sure it equals 5, and I'll plug it back into this equation and make sure it equals 1. Trust me, I already did it. It works out. And then I would have to do the same thing with my calculator, negative 2/5 and 11/5, plug it in for x and y in both equations. It is very, very common to end up with extraneous solutions when you have nonlinear systems.